Hi friends, I hope you had gone through the note I had posted in our group some days ago. Let me remind you that I said in that note that all of us should be ready with the prerequisites of complex numbers and the basic methods of integration. So I hope all of us now ready with fulfilling those prerequisites and refreshing all the materials I posted. And now we we are on the same ground to proceed from there, and we'll now start with the calculus of the complex function. Before we jump into the topic, I also want to make one remark here that from my experience I have known that it is not required to go through the theories in so much details. There is no need to go through the derivations again and again, because that is not something going to help us in the exams, the entrance exams. All we need to remember, yes, it is of course advisable to see how the results are derived and what were the logic behind them, but once it is known, there is no need to read it again and again, because that is not going to help at all. So by keeping that in mind, I will only be writing short notes, important definitions, and the results themselves. I will not derive any results. We will just use them. We will just make them in our notes so that we have to uh, remember them nicely. All right. So before we start before we start dealing with the complex functions, let us just make sure that we all use the same terminology and there is no confusion in future. So we describe z as a complex variable, and its structure is like this: x plus iy. All of us know this. X is called the real part, and iy together called imaginary part. Okay, and just like when in normal algebra we studied x and y being variables, and then when we studied polynomials we defined polynomial of x, that is p of x, and that could be anything. It could be quadratic equation or cubic equation or any order of the string of the variables. So if in case it was a quadratic equation, then it was 3x square plus 4x plus 7 or something like that. So here the variable is x, so it is p of x, and it is not always, since I said that it is polynomial of x, therefore I have written p of x, but I can also write it as a function of x. It is just describing the string, describing the polynomial in by using different symbols. But the function of x itself says that there will be a string of the some terminology which will consist of the variable x. So just like we had a variable x, and corresponding to this x variable we had a function of x, here we have a variable of z, and so we'll have a corresponding function of z. We call it w, and it has a structure like this. Here the structure of this f of z or the w is very much same like the variable itself. For example, this u is a real part of the function, and this iv altogether is called the imaginary part of the function. So it is very similar like the variable itself, but the difference here is that this variable, this real part, had just one variable x, and imaginary part had just a single variable y. Here the real part has a variable u, and u itself consists of x and y variables, so it can have x or y or combination of both. And just like that, v is imaginary part altogether with this iota, but v itself a function of x and y. So here it is not like this variable z, that this has x only and this has y only. Here u and v both are the functions of x and y. For example, let's say that f of z is equal to 3x square plus 5y plus I times 5x plus 9y cube. So here you can easily compare and say that this is a real part u and this is the imaginary part v. I'm sorry, this is the part v. V and u both are real parts, but v together with I, this whole become imaginary, but u and v separately are real parts. Okay, so now you look at the u term, then it is a function of x here, y here, and it could also be x, y, like that. And here also you can see. Okay, so this is how the f of z is structured. Now, how this function is described on a plane. Before we understand how the function is described on a plane, let us see how z itself is described on a plane. So z, or the z, is x plus iy. It has two variables. So we will have two x's corresponding those variables. One will be the x variable and the other one will be the y. And this is very similar like our normal xy plane. If we define a point here, let's say 5, 7, then we know that the x variable has a value of 5 and this y variable has a value of 7. But then in form of z, it will be written like x plus iy. X is 5 plus I, y, z is 7, y is 7. So this becomes z. So this is how we describe z on the xy plane. Okay, now once we know this, now we are able to study the limit of the complex function. In limit of a complex function, we take two planes. One is called z plane or z plane, and then there is another plane is called w plane. Okay, so z plane has a variable z x plus iy. So corresponding to this variable, for x we have x axis and for variable y we have y axis. W plane is f of x plane. So f of x has the structure of u plus iv. So it will have corresponding u and v axis. Now let me define some random region in this z plane, and in this region we have the center as z0. The radius of this region is delta, a very small variance from the z0 point. And if we have a z plane and we define a region in the z plane, then there will be a corresponding plane for f of z. Sorry, it is not here f of x, here it is f of z. So if I have a variable z, then of course I will have a corresponding value of f of z. So for one point z, there will be a corresponding point f of z. So it is just like if I plug in the value of z in this f of z function, this is the value of z. Okay, so if I plug this x and y in this function, I will get some final value of f of z. So for every variable z, I have a definite value of f of z. So in the graph, if I have some point z on the z plane, there definitely will be a corresponding point in the f of z plane, which will give the result of this z variable. So just like the one point, if I have a full region of many z points, there will also be a corresponding full region which all together will give the results of each z point. So for a particular value of z point, I have a particular value of f of z. So this is like 1-to-1 ratio. For every z, I have a corresponding value of f of z. And for every point within this region, I will have corresponding f of z point, which will be covered in this region. So this is called, and this of course has the center L, and the radius is epsilon, very small variance. This is called delta disk, and this is called epsilon disk. Okay, so since we are studying the limit of a complex function, f of z is a complex function itself. Okay, so we have to make sure that does it follow the limit. So when it will follow the limit, here is the definition, that it says that the function f of z is said to tend to limit L as z approaches to z0. Okay, so as z approaches z0, this f of z will also approach, it will also tend to the limit L. But when that will happen? For every epsilon, it will happen only when the f of z minus L is less than epsilon. For z minus z0 less than delta. Now what does this mean? If the f of z and L, this difference, is less than epsilon, that means this f of z point must be within this region. If suppose this f of z point was outside the region, then the difference between f of z and L would be greater than epsilon. So this is less than epsilon, that means we are restricting, we are constraining the f of z point to be within the region of the radius epsilon. Then only the difference can be less than epsilon. For z minus z0 to be less than delta, so here also the same condition applies, that z minus z0 has to be less than delta. That means z cannot be outside this region, otherwise it will not be less than delta, it will be greater than delta. Okay, so when does the limit exist? When f of z will tend to L for every z approaching to z0. When will that happen? It will happen only when f of z minus L is less than epsilon for every z minus z0 less than delta. That means that the f of z and z, both of them should be within their own disk. Z should be within delta disk, it cannot be outside this region, and f of z should be within this epsilon disk. If both the points, the z variable and the corresponding function. If both of them are within their own region, then the limit will come true and f of z will tend to L. So a function w equals f of z is said to tend to limit L as z or z approaches a point z0 if for every real epsilon we can find positive real delta such that this condition satisfies, then only we can say that this function is said to tend to limit L. Okay, so this means that for every z not equal to z0, that means z should be the different point from z0. So for every z not equal to z0 in the delta disk of z plane, there will be a f of z, and which will also be lying in the epsilon disk. So if you choose the point z within the delta disk, then there will be always a corresponding f of z, and that will also be within its own epsilon disk. It will never be outside the disk. So that is what it meant. For every z not equal to z0 in the delta disk of z plane, f of z has a value lying in epsilon plane. I'm sorry, epsilon disk of W plane, and then the limit will hold true, and when the limit z tends to z0, f of z will become L. So f of z will tend to L, then only this limit will come true. Okay, here when we say that z is approaching z0, then I always mean that suppose if this is the disk, z0 is the center, z is some point here, then I always mean that by reaching to z0 I can take any path. So in complex calculus, this is something different from the regular calculus, and is that in regular calculus, when we define a point P, let's say, and here is a point Q. So if I want to reach from point P to point Q, and this is x and y axis of course, then I will have to move delta x in the x direction only, and then I'll have to move delta y in this y direction, and that is how I can reach from pxy to q x plus delta x and y plus delta y. So if I want my this x coordinate to be from x to x plus delta x, I will have to move additional delta x in this x direction only, and then I will have to move delta y in this vertical direction only. It is never possible that I can move in any direction and then I say that it is just a delta y. If I want to have a delta y, then I have to restrict my motion in the vertical direction. If I want to have delta x, then I have to restrict my motion in the horizontal direction. But it is not in the complex analysis. It is not it is not like that in this complex calculus. If you want to move from z to z0, it is never you are never restricted like you have to move in this path only. You can reach from z to z0 from any damn path you wish to go, and still you will end up with the same result. Okay, so z approaches to z0 from any direction in the z plane. So this is something we should always keep in mind, because that this concept will be useful when we will understand the analytic function. So this has to be kept in mind, that here z approaches z0 from any direction in z plane.